Hello, this is Donna Nelson, University of Oklahoma, and I'm filming this for my Organic Chemistry 2 class that I'm teaching this semester. So we're going to be covering conjugated pi systems and pericyclic reactions in this chapter. It's chapter 16. We're using David Klein's textbook, and these slides will exactly parallel that textbook, except in a couple of instances, which I will note here. So, here are the sections, the different sections from this chapter. First, we'll cover, in the first video, we're going to have multiple videos for this chapter. First, we're going to have the different classes of dienes, conjugated dienes, electrophilic addition, thermodynamic control versus kinetic control. And so molecular orbital theory has been moved down into the next video. Then we will cover molecular orbital theory, an introduction to pericyclic reactions and Diels-Alder reactions. Then we'll cover the MO description of cycle additions, electrocyclic reactions, and sigmatropic rearrangements, which make up the large part of pericyclic reactions. So you can see that this chapter is sort of in two parts. The first part is includes reactions which are known to be or called charge-controlled reactions. And so these reactions, charge-controlled reactions, are charges that are dominated by, they're reactions that are dominated by the charges that are generated in the reactants. So in this case, the reactants that are charged are carbocations. They could be carbanions, but in this particular chapter, they're carbocations. The second part of the chapter is covers reactions which are orbital controlled. And so that's why I have moved the molecular orbital theory down into be in closer proximity to and presented along with those reactions which are pericyclic reactions and are indeed orbital controlled. So let's go ahead and start this. So the classes of dienes. There's three types of dienes. These are called cumulated, conjugated, and isolated. And here you see the bond line structures, and here you see the orbital components. So the one that is most common will be the conjugated ones, and in this case, you have sp2 hybridized carbons adjacent to each other in a line, and the p orbitals are all overlapping, as you can see here. And so these are said to be conjugated. These p orbitals overlap and interact with each other. Another type, which is not observed quite so often, is the cumulated diene. And here you can see one carbon atom, the one in the middle, is participating in two different pi bonds. And so here you have an sp2 hybridized carbon, an sp2 hybridized carbon, and this carbon is not sp2 hybridized. That's this carbon right here. You can see it has two p orbitals in it, which each p orbital is involved in a different pi bond. And so this carbon in the middle here is sp hybridized, and this has a linear structure here, just like alkynes, which have sp hybridized carbons involved. And then over here, the isolated dienes. These isolated dienes are separated by one or more sp3 hybridized carbons. And so they are not interacting, not in a significant amount anyway. And so these are the three types of dienes presented in different ways and also discussed down here. There's obviously no conjugation. There's no interaction. So this chapter focuses on conjugated systems and the special properties and reactivity associated with them. The dienes do not have to be just carbon-carbon pi bonds. Here, this is a carbon-carbon double bond, and this double bond is a carbon-oxygen double bond. So this is called an enone, because this is an alkene, this is a ketone, this is called an enone. So this would not be called a diene, but rather call it an enone. You can practice drawing these and answering questions about these using the conceptual checkpoint 16.1 in the textbook, and anytime one of the conceptual checkpoints is mentioned in any of my videos, you should always check your answer to the questions that are presented in the textbook using the study guide solution manual which accompanies this textbook. Now, the preparation of conjugated dienes. So, a sterically hindered base can be used to form a diene through an elimination reaction. So here, HBr is lost across this carbon-carbon bond, and a double bond is formed. So this is the second double bond in the molecule in this case. A very sterically hindered base is used. This is the T-butoxide. So this is potassium T-butoxide. And here this is sterically hindered. So the proton that this will abstract will come from the less sterically hindered end of the molecule, or the less sterically hindered carbon, and generate a terminal carbon-carbon double bond. That is not important up here because really there's only one CH bond or one proton that can be abstracted. But down here, you could have the possibility of having the carbon-carbon pi bond generated in between C2 and C3. And so it's important here to use the sterically hindered base to ensure that the terminal carbon is the one that undergoes deprotonation. And over here, the terminal carbon undergoes deprotonation. And so the carbon-carbon bond, pi bond, is formed on the ends of the molecule. And that gives you the 1,3-butadiene. The single bonds that are part of the conjugated pi system are shorter. This is 148 picometers, so that's like 1.48 angstroms. Here, this single bond that's in this system, and that's compared to 153 picometers, which obviously this is longer. And the reason for that is because you have sp2 hybridized carbons involved. So the sp2 sp hybridized orbital here is bonding with the sp2 hybridized orbital, but also you have some interaction between the two pi bonds, the conjugation. So let's look at this a little more closely. This will be review. So remember that an s orbital has 100% S character. Then you have the sp hybridized orbital. It's half S and half P, so obviously this is 50% S character. In sp2 hybridized orbital, it is 1/3 S, 2/3 P, so this is 33% S character. sp3 hybridized orbital is 25% S character, and the P orbital has 0% S character. So this is sort of logical. And so going back to what we were just discussing, the two bonds, the two orbitals that are overlapping here have some more S character here, because this is sp2 as opposed to sp3. And so the fact that they have more S character means that the orbitals that are involved in forming this bond will be shorter orbitals. They will lie closer to the nucleus, just like the S orbital. The electrons lie closer to the nucleus. So here these electrons lie closer to the nucleus. Any bond formed using the sp2 hybridized orbital will be shorter than a bond formed using the sp3 hybridized orbital. So let's look at the heats of hydrogenation that as used to determine or measure the amount of conjugation and the stabilization that is incurred in a diene because of the conjugation. So if we take 2 moles of butane, so here you have, obviously you have carbon-carbon double bonds, which are isolated. The carbon-carbon double bonds in the different molecules will have no interaction. And over here, the carbon-carbon pi bonds, which are in the same molecule, these are going to have some interaction. So no interaction between the different pi bonds, the different pi bonds in different molecules, as opposed to over here, these pi bonds are interacting through conjugation. And so the goal is to see what sort of stabilization this brings to the molecule. And so these, both of these are separately in separate containers hydrogenated. In other words, hydrogen is added across the pi bond, and here hydrogen is added across both of these pi bonds, and the amount of energy that's given off is measured. And so here you're going down in energy, and the product from this reaction and from that reaction, the products are identical, butane. And so if you measure the amount of energy that's given off in each of these reactions, it's possible to determine which one started at a higher energy point. So here, 254 kilojoules was given off in this reaction. Here, 239 kilojoules was given off in this reaction. And so we know that the former reaction started at a higher energy point because it gave off more energy to get to the same ending point. So we know that these two molecules combined are higher in energy than this one molecule. And of course, I'm just talking about the pi bonds in each of these two molecules. And so this shows that the difference is 15 kilojoules, the difference in energy. So that's the stabilization that is given by conjugation there. Sigma bonds freely rotate, as you remember. So, for example, in butane, where there are no pi bonds. The sigma, there's free rotation about all of the carbon-carbon single bonds. But when we have this conjugated diene, there's still rotation about the carbon-carbon sigma bond, the carbon-carbon single bond. However, it's a little bit restricted. There's a small amount of energy here that is needed to go from the cis isomer to the trans isomer, because here, when you rotate this, you're going to have to just briefly break the conjugation. So here, this cis isomer is all the carbons are lying in one plane, and here in the trans isomer, all the carbons are lying in one plane, and so you can have conjugation. Here, this is shown in the cis isomer. You can see all of the carbons lying in one plane, and there's interaction in the pi system. Here you can see it. All of the carbons are lying in one plane. This is supposed to be the trans isomer. And so there's interaction in the pi system here. However, when you go from the cis isomer to the trans isomer, there is the conjugation is temporarily broken, and that's the 15 kilojoules that we just measured a few minutes ago. The energy difference between cis and trans is 12 kilojoules, but right here at this transition state, at the highest point in the energy diagram, that's the barrier that needs to be crossed in order to go from cis to trans. So you have to go uphill by 15 kilojoules, and then you just go downhill, and it really doesn't matter how much you're going downhill, because this is the barrier that has to be attained going from cis to trans. And so if you look at the orbitals, what's happening, so this is an orbital diagram for this transition state. And notice how the carbon-carbon bond has been rotated so that it is no longer in the plane. It is sticking up, and you no longer have the overlap between the p orbitals. And so this is not really clear, but it perhaps is good enough for you to be able to see that the conjugation here, the overlap, has been lost. You still have the overlap between the individual pi bonds, but you do not have the overlap between the pi bonds to make it one system. And so that's why this is higher in energy than the cis or the trans. So let's review briefly Markov-Nikov addition of a hydrogen halide to a carbon-carbon double bond. Remember, the first step anytime that you put an organic compound in the presence of an acid, the first step is always protonation. And so that's the case here. And so the first step is proton transfer to the carbon-carbon pi bond, and that will happen in a way such that the carbocation that is formed is the more stable carbocation. This proton could go to either end of that pi bond, but what happens is it will go to the end that generates the more stable carbocation. And so this is the more stable carbocation that is formed, and then you have the carbocation in the presence of an anion, and so the two counter ions just collapse to give you the carbon-bromine bond formed. So an analogous reaction takes place with a diene, except you don't get just one product. You can get two products. And here, what happens is the first step is protonation, and then you'll have the positive charge is generated to give you the more stable carbocation, which will be the allylic carbocation, and then the bromide will move in for attack. And so let's look at that in more detail. Here we have protonation, which will happen in a way to give you the more stable carbocation, which will be the allylic resonance stabilized carbocation. And you can see the two resonance forms of that allylic carbocation here. Here's the proton that was just added. And so the primary carbocation, in other words, the proton adding at this end of the double bond to give you just the primary carbocation, which is not resonance stabilized, does not happen. This does not happen. This does. And so then what happens when the allylic carbocation is formed? Here we have the allylic carbocation formed. Bromide will come in to attack at the two positions of positive charge density. And so that's going to be at either end of the allylic moiety. So the bromide will come in here, bromide will come in here, and that gives you the two products that we just saw on the previous transparency. And so this is called 1,2 addition, 1, 2, 3, 4. This is called 1,4 addition, 1, 2, 3, 4. Okay, so the 1 and the 2 have, in this case, have nothing to do with nomenclature. It just means relative to each other. So by calling it 1,2 addition, it just means they're on adjacent carbons. Here, the 1,4 addition just means that it's purely relative to where the proton was attached. Here, it has nothing to do with nomenclature, so don't get confused by that. So, in the addition of bromine and many, many other electrophilic additions, you will see analogous reactions. So here, you can have the 1,2 adduct or the 1,4 adduct, just purely analogous to what you saw in the previous transparency. So this is very common, and again, this has nothing to do with the IUPAC nomenclature system. It's just relative to each other, where the two the two groups joined the butadiene. Now, thermodynamic versus kinetic control. This is very interesting. So at lower temperatures, you get predominantly the 1,2 adduct. 71% of the 1,2 adduct at 0 degrees. However, if you increase the temperature to 85, you get predominantly the 1,4 adduct. So the 1,2 adduct is the predominant product at lower temperatures. The 1,4 adduct, which you can see is the more stable adduct, you get at higher temperatures. And this is more stable because it's a disubstituted double bond as opposed to a monosubstituted double bond. So you might want to keep that in mind because we're going to be discussing that in just a minute. This is less stable, more stable. The less stable is preferred at higher temperatures. The more stable is preferred, the less stable is preferred at lower temperatures. The more stable is preferred at higher temperatures. So let's look at the reason for that. So here let's look at an energy diagram. The first step in the formation of either the 1,2 adduct or the 1,4 adduct, the first step is identical. So here, the attainment of the energy barrier, the protonation, which is the first step, to give the allylic carbocation is the same in either reaction. So this part of the pathway is followed regardless of what product you're going to. The second step is where the difference occurs. So now we have the allylic carbocation plus bromide in the presence of each other. And so you can see that the nucleophilic attack at the terminus of this carbocation, the nucleophilic attack leads to the 1,4 adduct, which is more stable because this is a more highly substituted double bond, and this is a higher energy pathway because the bromide is going to have to migrate down to here and attack at this other end. So rather than just once the proton attaches up here, bromide will be in a close proximity. It will have to migrate down here away from the proton and the initially formed positive charge. Down here, in order to form the 1,2 adduct, the bromide does not have to migrate through any solvent. So as soon as the CH bond is formed, the bromide is right there next to this carbon bearing the positive charge. And so you simply have the collapse of the counter ions. Now this leads to the less stable adduct, the 1,2 adduct. It's the less stable because this carbon-carbon pod bond is only a mono-substituted carbon-carbon pod bond. So here you have this interesting situation and unusual situation in which the higher energy transition state leads to the more stable product. So this is unusual in that the higher energy transition state leads to the lower energy product. Here, the lower energy transition state leads to the higher energy product. That's unusual. That is not what you see usually. So you can see these pathways are crossing, and usually they do not. Usually the higher energy transition state leads to the higher energy product, and the lower energy transition state leads to the lower energy product. And so you need to realize that this is unusual. Okay, so here this slide merely says that this is the more substituted alkene, so it is more stable. Less substituted alkene, it is less stable. At higher temperatures, you'll get the more substituted alkene at the higher temperatures, because what's happening is there is enough energy at higher temperatures. There's enough energy for the reaction to become reversible, and so once it becomes reversible, it can attain either of these transition states. And so it becomes reversible, and when that happens, the more stable product will predominate in the equilibrium. So as I mentioned earlier, the 1,2 adduct forms faster because once the CH bond is formed, once the proton is attached to the pi bond, the bromide is right there, ready to react. this is called a proximity effect. It does not have to migrate down to the other end of the molecule. Remember, these are taking place in the presence of solvent. And so the bromide would have to migrate through the solvent down here to the other end of the molecule. And so at lower temperatures, the reaction is under kinetic control, and you will have this higher energy product. At higher temperatures, you have the more stable product form, which is not shown here, but which would originate from this transition, from this mechanism that's drawn. So that's the end of the charge-controlled reactions, which are presented in this chapter. And so in the next video, we will start discussing orbital-controlled reactions.